Today is Mathematica Day. Mathematica Day in probability and statistics. My goal, at least in part, is to try to convince you that Mathematica is worth it. To this point, you probably haven't thought it's worth it. And again, more than just doing integrals, more than just doing calculations for you, which you could, do on Wolfram Alpha or something, but also understanding things ultimately through simulation. And yes, we can do simulation in a spreadsheet. And yes, you can do simulation in R or Python. But to tell you the truth, I don't know R and Python real well, but from what I do know of them, I like Mathematica better. Of course, it is costly. It's not free like R and Python are. So if you want to convince your boss to get it, they'll have to pay some money. So what is our goal? We're trying to understand continuous probability distributions with Mathematica, including the distributions from the last class. What are those? Those are the gamma, the exponential, the chi-square. We do want to review those. We also want to talk about the normal distribution today, the most important distribution for the entire course, the normal distribution, and maybe even how it's related to the binomial if we have time, and maybe even some user-defined distributions as well. But let's start by looking once again at the gamma distribution. The gamma distribution is important because it contains many distributions as what you might call sub-distributions, the exponential and chi-square being the most prominent. Again, here was its probability density function. Yes, PDF, not PMF, not probability mass function. Probability density function. And even though it looks complicated, to tell you the truth, for PDFs that are proportional to that expression, a power function times an exponential decay, it's as simple as it gets. Giving yourself flexibility to have two parameters, alpha and beta, that can affect the shape of the graph in various kinds of ways that we can explore. Let's go ahead and explore that a little bit right now with Mathematica. How do you get this PDF to show up in Mathematica? I have shown you this a little bit before. You can use the command PDF, probability density function, square brackets for inputs of Mathematica functions. Gamma distribution is built in. So you can start typing gamma distribution, finish it like that. And if you want to understand how to use this, click on the info button, go to the, well, what is this? This is the Wolfram Documentation Center, which you can get to also through the help menu, Wolfram Documentation. But clicking on the name of the distribution, gamma distribution, brings you to that page. You can also search for it by typing it up here. Gamma distribution, this with alpha and beta inside square brackets, represents a gamma distribution with these two parameters called alpha and beta. They're called a shape parameter alpha and a scale parameter beta. We don't quite know what those mean at the moment. Let's pick a particular gamma distribution. Let's pick alpha to be 2 and beta to be 3. Am I done? Can I enter this as is? And is it going to give me the formula? No, I need to go over here, put a comma and an X to emphasize that that's what I want the variable name to be. So the input for PDF consists of two things. The first thing is the distribution you're talking about, then a comma, then the variable name. If I enter this with shift return, I see the PDF when alpha is 2 and beta is 3. First point to try to understand it is it doesn't match what you see in the book. Does it match this formula? This would be an example, a simple example of trying to understand things with Mathematica. Does it match this formula when alpha is 2 and beta is 3? Alpha is 2, start over here. We should have x to the 2 minus 1 power, which is x. Hey, look, there's an x right there. E to the negative x over 3 power. That's what we have right here. And evidently, all this should simplify when alpha is 2 and beta is 3 to 1/9. Think about what you know about the gamma function already. The gamma function of 2 is the same as 1 factorial, which is 1. Gamma of 2 is 1. Beta to the alpha, in this case, would be 3 squared, 9. We are getting a 1/9 here ultimately. We want to confirm this is a PDF when x is positive. We can have Mathematica do the integral for us. If you're going to do it by hand, you'd want to use integration by parts. I could just copy and paste this in here. Copy and paste that formula in there. Notice the E is sort of a fancy looking E. You can also use a capital E instead. Don't use a plain lowercase e. That integral does end up equaling 1. Okay, so we've confirmed that's a PDF. What if I wanted the CDF in this context? Yeah, if you're going to do that by hand, by the way, you'd have to use integration by parts. I hope you realized with my hints on Moodle that with those integrals that were complicated looking, that you didn't have to do a bunch of integration by parts. You could use the gamma function and maybe substitutions to help you with those. What about the CDF? Cumulative distribution function. Just change PDF to CDF. Oh, but that doesn't seem so helpful. Gamma regularized. What in the world is that? Well, maybe I should try it like this instead. Copy and paste the integral. What is the CDF as an integral? It's an integral from 0 to x. Remember that? Why? Why is it an integral from 0 to x? In general, remember that CDF's capital F of x, always, 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 whether your variable is discrete, continuous, or something else. Is there something else? There actually is. There are mixed random variables that are somehow both discrete and continuous. Will we encounter such things? Oh, maybe for fun sometime soon we'll talk about one, but you won't have any homework problems about them. Always, 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 this is the probability that the random variable capital X is less than or equal to little x. No matter what your random variable is. The way this is computed is affected by the way your random variable is defined, whether it's discrete, continuous, or mixed. If it's discrete, you compute it as a summation. If it's continuous, you compute it as an integral. And if it's mixed, you do both a sum and an integral. Okay, I won't go into details. In general, you have to integrate from -infinity to x. The PDF, use a different variable like a t here. Why? Because you want to emphasize that the true variable for capital F is the upper limit of the integral. And this does imply, by the fundamental theorem of calculus, that capital F is an antiderivative of little f. The derivative of capital F is little f. That's why we use capital F and little f notation, just like in calculus. Is that true? Is that true for discrete random variables? No. Not in terms of the usual interpretations of these things. There actually is a way to interpret this in a similar way with discrete random variables, but it's a bit confusing, so I don't want to go into details. In our case, since our random variable is only positive, our PDF is only positive when x is positive, we could start the integral at 0. I change this to a t here and here. Couldn't Mathematica do this integral and not get gamma regularized? It actually can. Evidently, gamma regularized equals this thing, at least when x is positive, though that's not obvious at all. You might want to simplify this. I could do that / simplify or something, or maybe expand. Expand works better here. To expand it out. Does gamma regularized, whatever that is, simplify to the same thing? It doesn't seem like it would, but maybe. I don't know. Simplify. Okay, it's not seemingly doing that. It's being a bit more general when it thinks about the CDF of a gamma distribution, but evidently gamma regularized is this function. But maybe there's some values of alpha and beta where it would not be very similar to this, and that's why the Mathematica is trying to be more general. But if we plot both of these functions, well, let's plot a bunch of things here. Let's plot this function, the PDF. Let's plot this function. What I'm thinking by the integral is the CDF. And let's plot this gamma regularized as well. And maybe I should add 0.1 to it so we see it's the same. So we see it's like a vertical shift to the other one. X going from 0 to, I don't know, 5. Let's make these colored plot style, arrow, red, blue, green, or actually I like doing magenta. Actually, when I think of the word blue, I don't think of Blue's Clues, but when I think of magenta, I think of Blue's Clues. There we have them. Let's go further, maybe out to 20 instead. Yeah, that gamma regularized looks like it's a vertical shift by 0.1 units away from the blue graph. Let's make them closer. How about 0.01 units? They're practically the same thing, and they are indeed the same. They're the same function. It's just a different name for the same function. Gamma regularized is some more general function you've never heard of before. Okay? There's the graphs. Does this make sense intuitively? The red graph is let's go back to adding 0.1 to this just so we see the difference. The red graph is the PDF. Probability density function. Its outputs don't give you probabilities, unlike with discrete random variables, right? Discrete random variables, the probability mass function, little f of x, is the probability that capital X equals little x. These outputs don't give you probabilities. I can see, for example, when the input is 3.12, the output is 0.123. They don't give you probabilities. They give you probability densities. What does that mean? It means, for example, if you're wondering about x being close to 3.12, within, well, on some small interval of length 0.1 near 3.12, for example, if you wanted to find the probability that x is maybe between about 3.07 and 3.17, you get where I'm saying these numbers? 3.07 is 0.05 smaller than 3.12, and 3.17 is 0.05 bigger than 3.12. Maybe I should write this down. Oh, I lost my cursor. Can we get back to 3.12? There we go. The probability of being between 3.07 and 3.17 technically is the area under the curve, right? The integral from 3.07 to 3.17. But on a small interval near any given point, the output is approximately constant. I could approximate that area under the curve with the area of a rectangle, right? This is calculus 2. It's like numerical integration. Multiply the value of the function 0.123 times the length of the interval. 0.0123 would be your approximation for the probability. Is that right? It's an approximation. Let me copy and paste this integral here. What's a more precise value? Well, have Mathematica do it. 3.07 to, say, 3.17 like this. I don't need the expand anymore because I'm doing numerical integral. 0.0123 if you round it to the same number of decimal places. It worked. So the integral is giving you the exact probability for that exact distribution. The values of the function, the outputs, they're not probabilities, but if you multiply them times the probability densities, if you multiply them times small interval lengths, you get approximations to probabilities. You're really approximating the area under the red curve with the area of a rectangle. Base times height. The height is 0.123 and the base is 0.1 in this case. And the approximation gets better and better as the interval length gets smaller and smaller. That's what it means to be a probability density. You can see the blue graph is an antiderivative of the red graph. In other words, the derivative of the blue graph is the red graph. So for example, near this point where x is 5.89, the slope of this curve right there should be the value of the red graph at 5.89, which will be close to 0.1. The slope right here is close to 0.1. Doesn't look visually like it's close to 0.1, does it? It looks like it's closer to 1, but that's because the scales and the axes are different. Right? This distance on the x-axis goes from 0 to 5. A similar distance on the y-axis goes from 0 to 0.4. So the slope looks bigger than it actually is. If you drew a line here and approximated rise over run, you would get close to 0.1. And the slope is biggest when x is about 2.67. That's right about here. That's where the blue graph has a slope that's biggest. And it's an inflection point, actually, of the blue graph. It's concave up over here. And once you get past that point, it's concave down. The derivative of the blue graph, the CDF, is the red graph, the PDF. And the CDF is also approaching 1 as x goes to infinity. This graph goes out forever and ever and is always positive. Having the x-axis as a horizontal asymptote, it integrates to 1. The improper integral does exist. It does converge and it equals 1 because it's a PDF. Remember I said the other day, was it Tuesday or was it last week? I think it was Tuesday. In terms of simulation and statistics, you know, when would you want to use this red graph as a PDF in some real life situation? You got data, numbers, I don't know, maybe 1.02, 3.12, 4.74. I'm looking at the x coordinates here, 2.08, 0.87, blah, 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 blah. You gather data in some experimental situation in a good way, in a random way, based on random sampling, ideally. And you're wondering, I wonder if a gamma distribution is a good fit for these data. Is this red graph a good model for probabilities related to this experimental situation? Do areas under the red graph over any interval give you good approximations to the probabilities in this situation? Now, you might say that sounds like an impossible task. And yeah, technically speaking, you might say it really is an impossible task. But remember, in applied math, statistics, you're not after perfection. You're after good enough to get the job done and impress your boss and get a raise. Well, that shouldn't be your only motivation. Good enough to help the company and help people, help your neighbor, love your neighbor, care for people in the world by helping your company do better. And yes, that does mean making money because that's how they stay in business and that's how they help people. So there are statistical tests you can do that help you decide maybe the gamma distribution is a good idea here. They're not perfect. They don't tell you for sure it's a good idea. They just say it's reasonable, is what they end up saying, or not. And if you've decided to use a gamma distribution, then the question is, how do you find alpha and beta? Should I use alpha equal to 2 and beta equal to 3 like I'm doing here? Not necessarily. There's some statistics you can do to do that. Let's start to get a feel for those statistics and still relate it to the content of this chapter. Let's do some simulation. I always have to remind myself exactly how to do this. I know random variate is part of what I need to do. That is a fundamental command in Mathematica for doing statistical simulation, simulating from a distribution. Capital R, capital V. I believe probability distribution is also part of it, although I might not need that here. I think I can just, probability distribution is useful for user-defined distributions, but maybe I can get away with just using gamma distribution 2, 3 here. Maybe I should, let's copy and paste that in here. I'm pretty sure this kind of start will work at least. I'm not sure, will this work or not? Okay, it is working. When I enter this code over and over again, I get effectively Mathematica is sampling from this distribution, giving me statistical information in some mysterious way of numbers you would expect to get from this distribution. Now, I keep entering that over and over again, and I keep getting different numbers. What if I just want to get a sample size 100 right away? There we go. I put a comma 100. So this is supposed to be Mathematica's, not necessarily perfect, but hopefully good. Simulated sampling from this distribution, a gamma distribution where alpha's 2 and beta's 3. 100, a sample size 100 numbers there. Is there a way to confirm that it did a good job here? Well, there's various things you can try. We could give this picture a name here. I'm going to call it plot 1 and re-enter it. So I've stored the, I'll get rid of the gamma regularized now. I was just trying to convince you that they're the same thing. Okay, there's plot 1. You can use something called number line plot, I believe. Let me just look up number line plot. Actually, I'll do it in this one since I already got the it's zoomed in here. Number line plot, I believe, is what we want. One thing we could try using. Number line plot. What is the syntax for number line plot? Plot values on a number line with this kind of syntax. And you get this kind of plot. So we plug in into number line plot. We can get a basic dot plot by plugging in a list of numbers inside curly braces. Hey, here's a list of numbers inside curly braces. Should I copy and paste that whole thing in there? I could. I could also just put this inside the number line plot code. Like that. There we go. And if I re-enter it, I get a new simulation with new data. Because the random variable keeps getting used. Is it matching what we know the PDF looks like? Oh, put it up higher. Okay, I would like those dots to be down here. I'm pretty sure there's a way to do it. I'm not sure if I want to take the time to do it. We want to compare this with the PDF, not so much the CDF. Maybe, okay, maybe I should do, so this is, okay, let's rename things. Let's plot PDF and CDF. Let's just plot the PDF by itself as well. Plot PDF. Copy and paste, copy and pasting saves time. I'm just going to plot the PDF here instead of the CDF. We'll get a vertical scale that'll be smaller. And then when I combine the plots, that should work better. Or not. It's still up higher, and so we can't see it. Okay. Sometimes this happens. Okay, there is a way to get them scaled down to be lower, I believe, but I'm forgetting what the syntax is. Options. It's good that this kind of thing happens. Maybe plots, maybe spacings, maybe that does it. Spacing 0. Let's try the spacing 0 thing. Inside the number line plot. Yeah, that worked. The density function is supposed to be a measure of the density of the data. For example, and the area under the graph should give you the percentage of the data. For example, the probability that you're between 5 and 10 is the area under the red curve from 5 to 10, and that should be the same as the percentage of the dots between 5 and 10, approximately. Of course, it changes every time you do the simulation, but it shouldn't change by a ton. And where the graph of the PDF is higher, the data are denser. That's why it's called a probability density function. Maybe we should do 1,000 data points instead of 100. Well, that's a little hard to see. Maybe 200. Where the PDF's lower, the data are less dense. Moreover, we can compute the mean of the data. Mean. Wait a minute, we haven't talked about how to compute the mean of data before. What about a mean of the gamma distribution with alpha is 2 and beta equals 3 itself? It should match what we saw in the book. This theorem. Mean is alpha times beta. 2 times 3, 6. That's the mean of the distribution. What about the mean of the simulated data? What's a mean of data? Just add up all the numbers and divide by how many there are. In this case, 200 of them. Is this going to be 6? Probably not exactly, but close. Every time you do a simulation, you get a slightly different number, but they're all fairly close to 6. You shouldn't expect it to be exactly 6 because it's a simulation. But it's close to 6, confirming the theoretical mean from the distribution. How about the standard deviation of the distribution? Or can you do the variance? How about the variance? According to the book, the variance is alpha times beta squared, 2 times 3 squared, 18. 18. Is that the variance of the data? Again, every time I re-enter this, it does a different simulation. Should be close to 18. Well, that's a little further off. Okay, a bit more variability in the variance than there was in the mean here. If I did a random sample of size 10,000, it should be close to 18. Bigger samples give you less variability in things. Well, it seems to be underestimating the mean or the variance. That's actually not an accident. How about standard deviation? Can we do that too? Well, it'd be the square root of 18, right? How's Mathematica? We're going to write the square root of 18. Probably is the square root of 9 times the square root of 2, which would be 3 times the square root of 2. Yeah. Which is approximately 4.24 standard deviation of simulated data, close to 4.24. Now, if you didn't know alpha was 2 ahead of time and beta is 3 ahead of time, which you typically would not know, right? In real life, you would typically not know what alpha and beta are unless you were just guessing and happen to get lucky. It would really be the reverse process. You'd really be using your data, the mean variance of your data, to estimate alpha and beta. That's the way it would be done in real life. In the simulation, I'm pretending I know alpha and beta, then I do the simulation, and I see that the theory gets confirmed. In real life, you got to take your data, find the mean and variance and standard deviation of your data, and use that to figure out alpha and beta. Approximately, it's not going to be perfect. Different random samples give you different data, give you different means, give you different variances and standard deviations. We're talking right now about the deep connection between probability and statistics here that we're going to tease out a lot, especially once we get to chapter 7. But for the moment, you can use it to try to understand the reading. Yes, it's great to understand the reading as it is, but it's also a good idea to do what I'm doing here to understand it that way too. How about the other distributions? How about exponential distribution? Well, remember, exponential and chi-square are gamma distributions. Exponential is gamma with alpha equal to 1. But it's built into Mathematica as well, exponential distribution. We should probably look it up here. Where did I put that? Did I already get rid of that? Okay. Look it up here. By the way, we haven't talked about why Alpha was a shape parameter and beta was a scale parameter yet. Exponential distribution, lambda. Lambda is being used here instead of beta. Represents an exponential distribution with scale inversely proportional to parameter lambda. Where have I seen lambda with exponential distributions before? We saw it with this theorem. Consider a Poisson process with parameter lambda. What's a Poisson process again? Well, if we're thinking about counting occurrences of an event over an interval of time, under certain assumptions, which I never really got into much, that count will have a Poisson distribution from chapter 3, a discrete distribution, counting the number of occurrences of the event, like earthquakes per year or whatever. Lambda here is the parameter over a single unit of time, like a year. But, if you're doing it over 2 years instead, you could take the lambda to be over 2 years. So effectively, lambda is the same as k back in chapter 3. Just whatever scale you're thinking about, that's the unit scale, whether it's 1 year or 2 years or 3 months, like in the homework. Base your lambda off whatever scale you decide to use as a unit scale. W is not counting the number of occurrences, it's the time of occurrence of the first event. First event. Well, how is that different than maybe just the next event? The answer is it's not really different. It's the first event from the current moment in time. Yes, earthquakes have happened in the past, but now we are at a new moment in time, that is time 0, and we're thinking about waiting until the next occurrence, which we're now calling the first occurrence. W has an exponential distribution with beta, which is the mean. Beta is the mean, because the mean for gamma is alpha times beta, and alpha is 1 here. Beta is 1 over lambda. Yeah, if you average 5 earthquakes per year, let's make it 6 earthquakes per year on average, then on average, you're going to wait 1/6 of a year for the next earthquake. 2 months. So in Mathematica, is the lambda representing 1 over beta? Maybe that's not so clear yet. Let's go ahead and put a lambda in here, comma x. Look at this PDF. It does look different than the PDF in the book, not only because it's a lambda instead of a beta, but the role the lambda is playing is different. In the book, compare, lambda's like 1 over beta, both there and there. Yeah, lambda is 1 over beta. So if you want to use the built-in exponential distribution in Mathematica to simulate for exponential distributions, you need to realize that Mathematica is using 1 over beta for what goes in here. So whatever the mean is, say the mean is 10. Well, okay, say the mean is 10, you would use 1/10 for the lambda. That's an exponential distribution with a mean of 10. If you want to confirm that, you could do this. Whoops. 10. You could also do an integral if you wanted extra confirmation. Right? X times the PDF. This integral should equal 10. It does. By the way, if you don't know how to get an infinity, you can do escape INF, escape to make an infinity. Escape INF. You can also find infinity buttons on the palette. Yeah, the mean is 10. What about the variance? Well, first of all, the second moment. Okay, let's think about this. So the variance of a general gamma was alpha times beta squared. Alpha is 1 here, so the variance of an exponential is beta squared. Beta is 10 here. Lambda is 1/10. So we should get a variance of 10 squared, 100. Here's the second moment. That's not the answer. Take the second moment minus the square of the first moment. There's the answer. There's the variance of an exponential distribution. Beta equal to 10, lambda equal to 1/10. Can we simulate from an exponential distribution with a mean of 10? Sure. Random variate. Exponential distribution. I mean, I'm assuming Mathematica is doing a good job in these simulations. There's 200 data points from an exponential distribution with a mean of 10. If we put that inside a mean, it'll compute a mean of a simulated data set. Should be close to 10. Yeah, bigger the sample size is, the closer it is to 10. These are, I do even sample size 100,000. Yeah, I think it's doing a sample size 100,000 pretty quick. I think once you get to like 1 million or 10 million, it's less clear that it's really doing a random sample size 1 million. But I'm pretty sure that it will do samples of size 100,000 and not be deceiving you. How about calculating probabilities? Well, you can do that with integrals. Maybe it's most relevant to do that with the chi-square distribution. What again is a chi-square distribution? Okay, our book says chi-squared, which I say sometimes just out of habit, but I'm trying to say chi-square more often because you can say either one, but because you're not really squaring a variable, even though it looks like you are with the notation. Chi-square distributions are gamma distributions, where you take beta equal 2 and alpha to be little gamma over 2. Just a change in notation is all it is. Where little gamma is a positive integer called the degrees of freedom. And this is just a special notation for such a chi-squared random variable. This is the same as x. It's not x squared. It's the same as x in this definition here. Let's go ahead and see what Mathematica makes the PDF look like. Is it built in chi-square? Oh yeah, and Mathematica calls this chi-square. Although the D with the distribution looks, you could roll off your tongue as chi-squared. What are the inputs here? Chi-square distribution. V degrees of freedom, or maybe that's supposed to be a little gamma. You could call it a V. I think it's very similar to the shape of a Greek letter. Nu, N-U, nu. Doesn't matter, whatever. Okay, what's the PDF of a chi-square distribution if you have, like, say, 10 degrees of freedom? Looks like that. Looks kind of like a gamma, doesn't it? Let's confirm that it worked. So remember, the beta is taken to be 2. So that's why we have an over 2 there. We'd have a 2 to the alpha. What is alpha in this case? It's little gamma over 2. 10 over 2 is 5. Alpha is 5. Yeah, 4 is 5 minus 1. If I pick gamma to be an odd number, gamma to be an odd number, then alpha would be not a whole number. Look, you got a 9/2 power there. That's okay. I'll go back to 10 though. And capital gamma of, what's the alpha? It's 5. That's 4 factorial, 24, times beta is 2. 2 to the alpha power is 5 again. This should be 768. Yay. What if we wanted to find probabilities for the gamma distribution? Well, you could use Mathematica, and I'm telling you, you could use Mathematica on your homework now, or use the table. These things are set up to use the table as well. You could integrate the PDF. So for example, if you had a chi-squared distribution with 10 degrees of freedom, and you wanted to find the probability that you have a value between, say, 1 and 7, just integrate this PDF from 1 to 7. And approximate it. So 0.274 would be, with a chi-squared distribution with 10 degrees of freedom, the probability of being between 1 and 7. Let's also do from 0 to 7, say, or maybe I want to compare this with something in the back of the book in the table. Probability of being less than or equal to 7 is also very close to 0.274 because there's not much area under the graph between 0 and 1. Let's see if this one shows up at least close in the table. So now I'm paging back to the back of the book in the table. The table being finite in extent definitely can only give you approximations in most situations. So here is the table. We're after a chi-squared distribution with 10 degrees of freedom. You can see it says, yeah, chi-squared distribution. The gamma, the 10 degrees of freedom, is on the left. What are these numbers in here? They're not probabilities. Notice they're bigger than 1. They're numbers along the horizontal axis. The numbers up top here are probabilities to the left of the given number. So I'm looking for the number that's closest to 7. It's the 6.74. For a gamma distribution with 10 degrees of freedom, the probability of being less than 6.74 is very close to 0.25. 7 is a bit bigger than 6.74. Therefore, our answer is a bit bigger than 0.25. This number, 6.74, notationally would represent little chi square sub 0.75. If the degrees of freedom is 10, this is the 6.74. That's what the table means. Visually, if you draw the graph of a chi-square distribution with 10 degrees of freedom, it's probably going to look about like that. You could label this something like this, chi-squared sub 10. It's not literally the random variable, it's its PDF. And we've just found that the area to the right of 6.74, the area to the left of 6.74 was the 0.25 at the top of the table, because those numbers at the top are CDF values, they are areas to the left. But the subscript refers to an area to the right. So chi-squared 0.75 here, the 6.74 is that number, and this area to the right of it, this area is about 0.75. Because the area to the left in the table was 0.25. Confusing, but it's the way people use the notation.